Okay folks, in this video we're going to take a look at trigonometric curves. Sometimes they're called sinusoidal functions as well, so sinusoidal and trigonometric curves are describing the same thing. So just important thing to realize, first of all, we're going to be looking at these wave forms, these wave functions that sine and cos produce. But if we take a look at this seagull, and he's been moved around by the waves, he's actually describing a circular motion. And we're going to describe his motion. There's actually two kind of patterns been developed here. First of all is the vertical pattern. If we looked side on at the seagull, we'd see that he heads up and down in a vertical direction. And this produces a sinusoidal curve if we were to watch him over time as he went along, or as he goes around the circle. It'd be a more complete way of looking at it. But also what kind of sometimes you mightn't realize is there's also a similar pattern, but it's a side to side motion. It moves along the x-axis, and this also produces a waveform that if you were to watch, so the vertical waveform is a sine wave, and we'll discuss that mathematically a little bit more. And this one here then is a cos wave, where we're looking at the horizontal motion of the bird. That's a cos function. And we're going to look at both of these and the waves they produce. Just some of the terminology of waveforms. The amplitude is from the midline to the peak of the wave. It's not the whole lot. That's not the amplitude of the wave. The amplitude is from the midline to the peak. The wavelength is the distance between two peaks or two troughs. We have a crest, also I call them peaks, and we have the trough of a wave. And here we can see a sine wave being generated. So we're really watching, if you watch the dot in the middle, we're really looking at the vertical motion as a point goes around the circle. So we're watching a point here as it goes around the circle, but it describes, we're only watching, this is the eyeball looking from the left hand side, we're only watching the vertical motion of the wave. So we're going to describe this now mathematically, and to do this we use what's called a unit circle. A unit circle has a radius of 1, and hopefully it's obvious that as it passes around the circle at 0 degrees, we'll be at 1, 0. X is equal to 1 and y is equal to 0. At 90 degrees, we're at 0, 1. At 180 degrees, we're at minus 1, 0. That's the x value, minus 1. The y value is 0. And at 270 degrees, we're at 0, minus 1. Finally then, we actually end up back. When we complete the circle, 360 degrees and 0 degrees are kind of the same thing. You've completed the circle and we're starting again. So like I said, we're going to look at this vertical motion first. And if we get the sine of an angle, sine of theta, we're interested, we know the hypotenuse, and we're interested in this vertical motion, y. So the ratio that describes this vertical opposite theta and hypotenuse is sine. And now we know the hypotenuse is 1. This point, we're looking at a point as it goes around the circle. So at any point it's going to be at y. The vertical distance off of 0 is y. No matter where the circle is, no matter where the point is on the circle, it would always be described by y. So now we can write, well, the sine of theta is opposite over hypotenuse. So that's just equal to y. So the sine of theta, in order to describe the sine wave, the sine of theta, we only look at the y coordinate of a point as it travels around the circle. And that's what we're going to do next, but we're only interested in the y values as it travels around a circle. And we take a look. So same unit circle. We're only interested in the y values because we're describing that vertical motion. And now at 0 degrees, the sine of theta is 0. The y value is 0. At 90 degrees, the y value is 1. At 180 degrees, the y value is back to 0. Remember, we're only watching the y values. At 270 degrees, the y value is -1. And at 360 degrees, we're back where we started, and the cycle begins again. So we're going to plot these now. We're going to draw a graph. Plotting out our points. But again, we're only looking at these y values as we go around the circle. And that's what we do on the next slide. So at 0 degrees, the sine of theta is 0. So this is this point here. 0 degrees, our y value is 0. At 90 degrees, our y value is 1. At 180 degrees, our y value is 0 again. This is just repeating what I said on the previous slide, but now we're kind of mapping the motion against the angle. So our input is angle and our output is amplitude. At 360 degrees, we're back where we started. And this is what gives us the classic sine curve. The main thing to note from a sine curve is it's smooth all the way. You never use straight lines. It's a very smooth curve, but a sine wave starts at 0. That's the crucial element to remember about a sine wave. It starts at the midpoint, at 0. Yeah, that's the best way to describe it. And it heads upwards. Just a brief, if it was minus sine x we were looking at, it would look similar, but the only thing is the direction of motion at the start. For a negative sine curve, we start at 0, but we head downwards. And now that's one full cycle there, as long as we've got as far as 360 degrees. Now we're going to take a look at the cos wave. And here we're watching the horizontal motion. If you remember the seagull, we're watching his horizontal motion. So this is like the eyeball being down at the bottom. And watching that horizontal motion of the seagull as he goes around one cycle. It produces a similar looking curve to the sine wave, but there's just a few notable differences. Here's our unit circle. We're interested in that horizontal motion. So if we were to draw this point, this is any point on the circle, it'll be xy. But we're interested in this bit, the x value. And now we know the hypotenuse. We're interested in x, the relationship that joins these in terms of theta. Remember theta now, x is adjacent to theta. 1 is still the hypotenuse. So the ratio, the trigonometric ratio, which describes adjacent and hypotenuse, is cosine, cos. The adjacent length is x. Our Our hypotenuse is 1. So this is just to reinforce that if we're looking for a cosine wave, we're watching the horizontal motion of a point as it travels around a circle. Sine wave looks at the vertical motion. So similar now to the sine wave, but now we're looking at the x values. So at 0 degrees, remember this point was 1, 0. Our x value is 1. At 90 degrees, my x value is 0. At 180 degrees, my x value is -1. Sorry, no, that's right, that should be in there. At 270 degrees, my x value is 0. And at 360 degrees, I'm back where I started, my x value is 1. And similar to earlier, we can map this out when we plot degrees or radians on this axis. This is our degrees, and this is my amplitude here. So we take a look. At 0 degrees, cos of theta is equal to 1. 90, cos of theta is 0. 180, cos of theta is -1. 270, we're back at 0. And it's very important with a cosine wave is you finish where you started. So we started at the peak of a wave, so we must finish where we started. Don't be tempted if you're sketching a curve to drop it back down. That's what a lot of students do, and you lose significant amount of marks because it shows you don't understand the wave fully. So that represents one full cycle. Now, if we were to look at minus cos x, in this case, we start at the trough of the wave and we finish back at the trough of the wave. So that's what a minus cos x curve looks like. So now you can just see actually both graphs being produced here. The blue line is looking at the horizontal motion, and the red line is looking at the vertical motion. So as a point goes around the circle, it's producing a cos wave of the horizontal motion, and it's producing a sine wave off of the vertical motion. And we're going to kind of both sketch these and analyze them then just in the next few slides. So if we're asked to sketch a curve, it's important to understand what each part of the function means. So first of all, is it a sine wave? Well, as we saw, a sine wave starts at 0 and heads upwards. Or is it a cosine wave? That starts at the peak. That's the first question you ask. What's this bit? The next bit is it negative? Remember I said a sine wave, negative sine wave, starts at 0 and heads downwards. Or a negative cosine wave starts at the trough of the wave and heads upwards. The value A is the amplitude of the wave. Remember, the amplitude is from, this is the amplitude. So that's the value A. And finally then, the value B here, this tells us the number of full cycles we need to complete in one revolution. So how many waveforms, how many full waveforms would there be in one full revolution of a point traveling around a circle? So probably best explained by example. Now you'll have to forgive me because I'm drawing freehand here and I'm drawing at an angle, so sketch the curve y is equal to 4 sine 2x. Well, first of all, it's a sine wave, so I start here. It's positive, so I know I'm heading upwards. My amplitude is 4, so I'm going to go right up to the top and right up down to the bottom. And I need to complete 2 full cycles by the time I get to the end. So you're always looking for a nice smooth waveform. Sorry. And now that's, again, I'm not going to spend ages drawing them again and again, but that's the general idea. That's what my waveform should look like. So now we're going to sketch the curve y is equal to minus 2 cos 3x. So I need to fit in 3 full cycles. So I'm just going to mark off, there's about 120, there's about 240. So I need to kind of fit in a full cycle in here. It's a minus cos curve. So I start at the bottom. I start here. And my amplitude is I'm going from plus to minus 2. So my first wave should finish about here. My second wave should finish about here. It's just to try and make it a bit neat. I have to try and divvy this up equally. And my third, I'll just move that over a little bit. So it takes a little bit of planning and stuff when you're doing this, but we'll see how we go. So there's one full wave. There's 2 full waves. And there's 3 full waves. So that's minus 2 cos 3x, and we have 3 full waves in there. 1, 2, 3, yeah. This one looks a little bit trickier, but don't be put off. It's the same idea. It's a negative wave. My amplitude is 1.2, so we'll just say that's about from here to about here. Now, this is important. It's a sine wave, so I start at 0 and I head downwards, but there's only half a full waveform. So remember, a sine wave, a negative sine wave would look like that. So half a sine wave is just going to be this bit here. So when I draw this, it looks nothing similar, but I'm just going to go down here. There's my lowest point. And that's us there. It's only half a sine wave. My amplitude goes down to 1.2. So that's sketching the curves. We'll just take a look now at if you're asked to determine the function. It's easier when you're given the curve than actually sketching it. So first of all, we're asked to determine the equation of this function. Well, the first thing is we ask ourselves, well, what's nature, sine or cos? We can see it starts in the middle at the midpoint, so it's a sine wave. It's heading upwards, so it's a plus sine wave. My amplitude goes up as far as 2. So I've determined this much, and then there's 1 full cycle, there's 2 full cycles, there's 3 full cycles, and that's my function there. Here's another one. Now this time it starts at the peak of the wave, so I know it's a cos function and it's positive. Our amplitude goes up as far as 4 and down as far as minus 4. And we can see there's 2 full cycles in the curve. So sorry, I'll scribble that out. Y is equal to 4 cos 2x. That's the nature of that function there. Now be careful of these. These ones are on Moodle. These ones are actually showing us 2 full revolutions of a circle. So it actually goes from minus 2 pi to 0. That's 1 full revolution, and now there's another revolution here. So when you see these ones on Moodle, you ignore the left hand side. We're only looking for 1 revolution. So now we can see we're starting here. It's minus cos. The amplitude is 3. And we can see there's 2 full cycles then. So it's very important with these ones, guys, when you see them, you only deal from the 0 out as far as 2 pi. That's the relevant part of this problem. What this question is trying to show you is that these waves continue forever and ever. So don't expect it to arrive in a little neat package from 0 to 360. It'll very often arrive as a continuous waveform, and you have to say, right, I need to start at 0. That's where my analysis begins, when at 0 degrees, and then take a look at one full revolution, either 360 degrees or 2 pi. Here's another one. Looks a bit tricky, but again, ignore the left-hand side. I can see, well, it starts at the middle at 0, so it's a sine wave. It's positive, and we can see there's only half a full cycle. So there's our function there. Y is equal. The amplitude, is 2. I missed that out. And that's our function there. So I hope those make sense. Now, there's some for you to try. So here's the first one. Pause the video. When you're writing out your function, I'm just writing out something random here. Make sure there's no spaces. 2x. If there's just one full cycle, guys, just write it as x. Don't write it as 1x. So that's how you write your function when you need to enter it into the editor. No spaces, no brackets. Here's another one for you to try. Again, pause the video. Another one now. This one is the one you'll encounter on Moodle quite frequently. Again, remember to ignore the left-hand side and perform your analysis. Again, pause. And just one more then, final one. Have a wee go at that one there. So once you get the hang of them, they're fairly straightforward. Like it's, analyzing trig curves can be, once you know what you're doing, can be quite straightforward. And it's not the hardest quiz in the world, not the hardest test, the one on Moodle. Okay, so now we just take a look at, here's lots of functions going on at the same time. I like these animations. And now we're just going to take a look at a few real-world examples. So our electricity in Ireland and Europe, our electricity is supplied at 50 Hertz. That's the frequency. That's the number of full waves per second. So here the period, if we divide a minute by 50, we'll get, a waveform passes every 0.2 seconds. So if you could watch the electricity coming out of your plug, your socket, this is what you'd see. And coming out of your residential socket, we have what's called single phase electricity. There's only one waveform arriving at any one time. If you were working in industry or in a commercial premises, they'd often have 3-phase electricity. And we just take a quick look at 3-phase electricity. We won't do any maths on it, but it's just to try and understand it. Here's single phase voltage. This is what it'll look like. Now, if we were to bring in another phase, say we needed more power, we could bring in another phase, which would look like this. This is 2-phase. And what's happened here is they call it a phase shift. So this little bit inside the brackets here has shifted the starting point by 120 degrees. So there's the starting point of the second wave. We can take a look at 3-phase, which is most common. And here we have the first phase starting, and then there's the second phase. Or the third, sorry, that's the same one. So I know it's not that one. So here's the first phase starting. Here's the second phase starting. Yeah, and then here's the third phase starting. And what this simply allows to do is deliver a lot more power. So commercial and industrial premises obviously need a lot more power than a domestic premises. So this is how the ESB gets the electricity to those people. Rather than having three separate lines and three plugs going into a machine, you can deliver 3 times the power by using three-phase electricity. And obviously it's all waveformed, and managing these then is the job of EirGrid and people like that up in Dublin, the Central Control Centre. Very interesting place. I've visited it a few times. GPS, so how your phone works, is with trigonometry. So your phone kind of figures out where you are, your distance from a base station. This is the base station, this is where you are. So it knows you're a certain distance and a certain angle away, and it can turn that then from, this is called polar coordinates, which we haven't really looked at. It's a big part of trigonometry. It's kind of how you find out where you are at any point. But with a little bit of maths, we can turn from these polar coordinates. This is what your phone and the base station is communicating to each other. But then your phone will translate that into what's called Cartesian coordinates. These are our XY coordinates, which we're more familiar with. And that'll tell you then where you are on any kind of a map. So all of this is governed by trigonometry. Here's the polar bit here with the dotted line. And then, like I said, we go from polar to what's called Cartesian. We don't cover any of this, but it is a big field of maths in itself. Anything you look at is governed by waves, because light, any kind of light, is a waveform. Each color has a different wavelength. This is the visible spectrum. So this is where our sight lives, within this spectrum. And then there's an electromagnetic spectrum, which covers a much larger range. The visible light only takes up a tiny part of this spectrum. And this is where X-rays, as the wavelength gets very short, we're into X-rays, gamma rays. And as the waves get very long, we're into radio waves and microwaves. So an awful lot of communication, sight, sound, are all governed by waveforms. Sound waves. So to create a sound, we have to set a matter in regular motion, creating waves of specific frequency, which we hear of sound as a particular pitch. We'll be looking at sound and stuff a little bit later when we're looking at log functions. Heartbeat is another kind of complex waveform produced by the cyclical opening and closing of heart valves. And just a few other ones: swinging of a pendulum, crankshaft in a motor, rotation of a Ferris wheel, or a big wheel as we call it, fluctuating hours of daylight throughout a calendar year, patterns of energy use in a house, and tidal fluctuations. These are all governed by sinusoidal or trigonometric functions. So looking at a crankshaft in any kind of an engine, internal combustion engine. Person on a Ferris wheel produces a sinusoidal curve over time. Temperature fluctuations, seasonal fluctuations, produce rough sinusoidal waves. Tides, very complex, but lots of different patterns of waveforms for tides, but it depends where you are in the world how the tide operates in that area. But it's all governed by sinusoidal forms, waveforms. And then a lot of business models take a look. They figure that economic and employment cycles are also of this nature as well. But this is a field well beyond our remit. We're into the world of business and stuff, and it's not governed by natural circumstances, so these wouldn't be as kind of pure sinusoidal as some of the ones we looked at on the previous slides. So that, folks, takes us to the end of trigonometric curves. So thank you very much for listening, and we'll finish up there.